specifically.
Yes.
Where he got in trouble with, was that if you add up, you could determine the age of the earth according to the Christian Bible, which everybody was reading then.
Yep.
It was 4,400 years.
Yep.
Which is a ridiculous.
Or the longest one was 6,000 years. Yeah. And now he's saying way more than that. And the reason is we know well, rats. We know that that the word evolution and the idea of animals changing had been discussed for a long time. And it was only Darwin's theory, which included natural selection, that sort of made any sense, as opposed to the other alternatives. But you're right. If you were living in that time, the Earth was 4,000 to 6,000 years old, depending on the. There were two main ministers, reverends, priests, pastors. Oh dear. Okay. Now, the reason he paid so much attention to the layers was that he was working for miners, and he wanted to know where the minerals were, and this is the same sort of thing that people do with when they're trying to find a place to drill for oil. If the layers are consistent, you can say, for instance, layer 35 is going to be chalk. And chalk is made up of the tiny skeletons of the sea-dwelling creatures, the diatoms. And it's very soft. And so water can seep through it. So you needed to know where those were so you could tell the person mining some other minerals, don't go below this level because you're going to have leakage and so on. So the layers had to be identified for what type of rock they were. Now, most fossils are found in sedimentary rock. Sedimentary rock, sediment, stuff coming down on top of it. Usually, we've found fossils in one of 2 or 3 different places, but in terms of stratigraphy. But usually, it's in a place where there was once an ocean. And with time, the little algae and things up here die and they fall to the bottom. And at the bottom, you have the bottom of the lake. Well, now you've got little things that are covering it, little dead things that are covering it from the top. They decay, leaving only their skeleton. Well, time goes on. The layer down here gets more. Let's say that the lake is evaporating because of weather change. And you end up with a layer down here of the diatomaceous material. If a fish died between this time and that time, and it's a flounder, let's say. It died and it buried itself in the sand and it wasn't eaten. What that would mean would be that somewhere in here is going to be a fish skeleton. And it's going to be compressed as more and more of the stuff lies on top of it. And that's where the mineralization of bones and things comes into play. You can sort of see that as time passes, it gets squished harder and harder and harder, and that has an effect on the type of fossil that you find. But the idea of faunal succession and superposition. Superposition means new things first, old things last, just by common sense of the fact that he was looking at rock that he knew was made of layers. Everybody got that? Does that make sense? Any questions on that one? Okay. Now we're going to turn to the earth and the sun, maybe, depending on time. I'm gonna give myself 15 more minutes and take questions.
We have pages 1 and 3, but the 2 on the back of 1
Isn't there?
Isn't there.
I said two-sided. I'm sorry. I will.
If it's for next week, it'll be done anytime.
Okay. Well. No, I wish you had this, but well. Anyway. Prior to satellites, how did we know how big the Earth was? And how did we know what it was made out of? Well, there was a brilliant woman whose name Becquerel, who looked at the Earth and looked at places that had earthquakes. And what this woman did is just unbelievably brilliant. She took the readings of the same earthquake from different places on the globe, and she did what the CAT scan does. It interprets all of the ways that is possible. And she, and I should look up her name, she decided that the only way to get this kind of picture was to have a solid core of something. So that when the sound wave, when the earthquake waves spread out, if they hit the core, they would bend away. It's like light going into water with the pencil in it. It bends away, so it comes out here.
Refracted.
Refracted, yes. Thank you. So this, south of whatever we're calling the earthquake, she could say there's a core inside the Earth, and based on timing and other things, she could say this is liquid and that's solid rock. That's all she could say. I thought that was astounding. By just by looking at the tracings of the earthquakes, she was able to come to that conclusion. Brilliant find. Then came along better equipment, and we discovered that the Earth's center is not only has a center, but also the center has 2 layers to it. So you have a solid iron core, liquid iron core, and since I'm going ahead of myself, and also because of the transmission time, they were able to determine how long it took for that to get to the sensor, and by using the duration of time to get there as well as the tracings, they came out with this image of what the Earth is. And they said, okay, the Earth is hot. Why is it hot? And there were a lot of explanations, but it turns out that the Earth is hot primarily because of radioactive decay in the core. It was originally heated up by bombardments, meteors, and other things that aggregated to become the Earth. I should probably just get rid of this distraction. Before that, people thought things like that the sun burned coal, and Lord Kelvin did a calculation on if the sun was made of coal, how long would it burn, and it was pretty obvious that it wasn't coal. So we have the Earth's heat from things colliding, and we have the Earth's heat continuing based on radioactive decay.
Wasn't that the Earth formed from the sun, a piece of the sun, let's say, flare, and that was hot, and that created...
Yeah, no.
No?
We think astronomers believe, because astronomy looks back through time, because it took time for the light to travel to you. So if you get a big enough telescope, you can see things, you can see one star here and another one there and another one there, or excuse me, galaxy. And here you'll see a nice spiral galaxy that looks an awful lot like ours. Here you'll see sort of an ovoid shape of just not really much of anything. It's a blob. And up here, what you see, oops, I switched these. Okay. What you see here is just a blob. It doesn't have much of anything. But in here you start to get structure, and you start to get planets formed from this dust. The dust from the solar system was stuff that was blown out of supernovae and novae nearby. Our star, I believe, is a third-generation star. So stars blew up and formed a star, that blew up and formed another star, that blew up and formed our sun. You're asking about the planets, though. If you look back through the telescope, what you see when you do find a star that has planets around it, what you see is first just a cloud of dust. And then what happens is the dust particles, little and big, start to aggregate. They start to get pulled in. It starts out as a perfectly spherical mass of, I'm trying to make you think this is a sphere with my fabulous drawing techniques. But you have a big sphere, and the dust was blown out from somewhere, right? So it has some momentum. But gravity is pulling these things together. Well, gravity pulls the things together towards the center from all directions, but those particles have motion, they have momentum. And you may have heard of the conservation of momentum or the conservation of angular momentum. So what happens is this big blob, which just has lots and lots and lots of little particles, starts to spin. As everything comes to the center, the average spin, the average momentum of all of those gazillion particles is what determines that we have a rotating solar system. But it's rotating dust. So it doesn't have anything of interest in it yet. It's just, a cloud, basically. But it's spinning, and the larger pieces in it, this is our solar system we're talking about, the larger pieces in it will go in towards the sun, and the smaller pieces, some of them will go into the sun, the asteroids hitting the sun, or the asteroids hitting Jupiter. Remember the Shoemaker-Levy meteors that broke into 9 parts and smashed into Jupiter, and we can still see where some of those hit. Pretty cool stuff. But what happens is that you have dust. It tries to come to its gravitational center, but it still has motion, so it starts to circle around that gravitational center. Gravitational center gets most of the stuff, but not all. So you end up with planets in orbit around the sun. So you've got the sun, which is black, great, Mercury, Venus, Earth, Mars, and I don't even Jupiter. But anyway, it's that's the way the planets are formed. And that's also the reason that the planets all are almost all in the same plane and are all going in the same direction.